Let us now see what would the energy be stored in a capacitor when we have charged the plates to plus Q and minus Q. To think of this energy storage, like how did we really charge this plate? We connected it to a battery. And what did the battery do? The battery took some charge from the bottom, raised it up, and put it next on the top part. Remember, if you go and you look at those games, there are these games where, or these toys, where you have an elevator which picks up the ball and brings it to a height, and then you have a maze over which the ball can fall down to come below to. That is what the battery does. The battery is like battery of the source is like that elevator which picks up the charge from below, positive, and lifts it and gives it to the other part. This marble maze you have is the circuits you have been doing, which allows these balls to fall down and come back to the bottom. But in the capacitor, what we have said is that we have put a stop here. So these balls just start collecting and are not allowed to go any further. And that's what a capacitor is doing, that the charge starts collecting here and it gets devoid on the back part. So I want to calculate what the energy stored in this is. And since we have been calculating energy stored based on the work we do in moving charges, so I will use the same thinking here too. So let's assume that we have, and let's just that we have a capacitor. I'm just drawing a parallel plate, but this could be any two arbitrary shapes. It does not change. And instead of the battery moving the charges around, let's assume that I go steal a charge from the bottom, let's call it dq, and then go and deposit that charge up. Originally, I have 0 or total charge at the bottom and 0 total charge on the top. The two conductors are neutral. They have equal number of electrons and protons within them. I steal some positive charges from the bottom and I lift it and put it on the top. The first time I do it, I don't do any work because there's no forces happening on me. But as I keep on stealing, so once I steal it, I put dq, then I come down and I steal another dq and I start putting it up. So let's say I have already put a charge q on the top, and thus there is charge minus q on the bottom. And in doing that, this has a capacitance C. I have created a potential difference, a delta V, which would be Q by C. The first time I stole the charge dq, there was no potential difference. I didn't do any work. But as soon as I start depositing charge on the top, stealing charge from the bottom, I start creating a potential difference. And now when I have to go and pick this charge dq and move it up, I would have to do work against this potential difference. So the work which I would have to do in moving dq across a delta V, that work would be given simply by the charge I am moving across the potential difference. So that would be Q by C and dq. And what do I want to do? I want to keep on doing this till I completely charge it to plus Q. So the total work I would do would be an integral of this work as I move Q from 0 to capital Q. Keep on summing it up. So I take a step, move a charge, come down. When I'm coming down, I don't have any charge with me, so I'm not doing any work. Come down, steal a step, put it up in these small increments of dqs till I have able to charge the top plus q. So what would be the total work I would end up doing? The total work I would end up doing would be 0 to q integral of q by c dq, which would simply be half q square by c. And the work which I did, I was an external agent, which is the same as me acting like a battery. This work which I did as an external agent, that would be the energy stored in the capacitor. And this would be an energy stored in electrical fields. So the energy stored UE would be simply be given as half q square by c. That's one form, but we also know q is a CV. So if I substitute it over here, we get another form half CV square, where V is the potential difference across the conductors. So we have these two forms. You will see this in ECE 140 also. Most probably in ECE 140, this is the form you are going to use, half CV square. But for our cases where we are trying to understand how charges are moving around in capacitors, both these forms can be helpful. Thinking in one or the other could be helpful. There's another form you can write, which for at least this course is not really that useful. See, we can also write this as half q by c, which is the potential, so that becomes half qv. Let's see a couple of cases to make to understand why sometimes using this form is helpful and other times using this form is helpful. Let me take case one. What I have, we have a conductor or capacitor, and let's just use parallel plate capacitor for our thinking, but whatever I'm doing is true for other capacitors too. Let's say Originally, this capacitor is, the plates are separated by a distance d. That's the original. So my initial Ci is going to be A epsilon by d. A being the cross section, d being the space and space between the two charges, and epsilon being the material between them. I take a battery and I connect the battery across it. I would end up charging the capacitor plates, and the charge I would get here, Q, let's call it Q initial, that would be C initial V. Now what I do, with the battery connected, we move this plate up. And remember, I told you there are places or there are sensor systems where we move these capacitor plates, which changes the capacitance, and we are looking for that change in capacitance. So let's assume that I have the voltage source still connected, but now I'm not drawing it to the same scale as the up. We have increased this distance to be 2D. Now what has happened, your C final in the final stage has become A epsilon by 2D. I'm assuming that the material is somehow stretchable and keeps the same epsilon, or you can call it air, then there is no conceptual difficulty. But my capacitance in the final stage has changed. My capacitance in the final stage compared to the initial stage has become half because the distance between the plates has doubled. However, the battery is still connected. The potential difference across the two plates is the same. Question is, what happens to the final energy compared to the initial state? And in this case, because your V is remaining constant, V has not changed between the final and the initial stage. Has Q changed? Yes, Q has changed. Q final now is C final times V. Q has changed, but my V has not changed. Thinking in terms of half CV square makes our life very straightforward. My initial energy here is half C initial V square. My final energy is half C final V square. And if I want to see what happened to the energy, U final by U initial would be C final by C initial. And we have already said that is half. So my U final is going to be the initial energy, half of it, when I doubled the plates. The energy stored in this system has decreased. Why has it decreased? The potential drop across the two capacitors plates is still the same. Where has this energy gone? What has happened can be seen here. Your final charge is half your initial charge. You increase the distance. Now for the potential difference, You have to go double the distance, and thus the electric field which should be coming down should become half of this electric field, so that the potential difference is maintained. The battery is a very strict rule. The battery is saying that the potential difference across the two ends has to remain the same. So what should happen? The charge on the conductors has to decrease. What would happen? The charge has to travel backwards. The battery is going to say, you do not need as much charge now, send me the charge. And the battery is doing negative work. Battery really wants to send positive charges this way. When battery is sending positive charges forward, it's doing positive work, but now it's saying, you do not need that much charge. Please send me some charge back now. I will take some of the charges back because you have doubled your distance. And in taking the charges back, it is doing negative work. This is your external agent. That external agent is doing negative work, and your energy is decreasing. That's why we see the energy decreasing in this case. Let's take case 2. Similar experiment, but now what I do in step 1, I have the same plates, distance d apart. I connect a voltage source and I charge this Q initial, where Q initial would be C times C initial V naught. C initial, we have said, is A epsilon naught by D. I'm just assuming this is air in the middle. In step 2, I remove the battery. There is a switch. I open the switch off. So I remove the battery. But this charge which is present here, that charge just remains the same. Let's put that charge, let's call that charge Q. So Q is Q initial, and I have a minus Q charge here. They are attracted to each other. They want to try to come and meet on this path, but they're not allowed because I have air in the middle. I remove the battery, they don't even care. They just get captured on the capacitor then. Now what I do is I take this plate and I move it up. I increase the distance d by 2d. So my C final is again the same as we had previously. C final by C initial is still half. Now what happens to the energy? Well, in this case, if you notice here and here, this charge Q and minus Q is trapped. You still have charge plus Q here and minus Q here. That charge has nowhere to go except sit on these conductor plates. Now, charge is remaining same across these different steps. It's actually going to be easier to think in terms of Q square by C initial of that form. Now I should use, at least it would require less mental gymnastics to see what would happen by considering that equation, half Q square by C. So my initial energy is half q square by c initial. My final energy is half q square by c final. Q remains the same. Now what has happened? If I look at u initial by u final by u initial, this becomes c initial by c final, and that is 2. In this case, when the battery was removed and I moved the plates away, I increased the separation between the plates, the stored energy increases, it doubles. In the previous case, when I had the battery connected and I moved the plates, the stored energy decreased, it halved. But if I have no battery connected and I increase that distance, then the stored energy doubles. By appropriately using this equation, we can get to the answers very, very quickly. Now, what has happened here? Where is this energy coming from? Where is the energy coming from which is increasing the system? Remember, there is electric field across this region. There are forces between the two plates. When I have moved, whatever is the electric field I had here is still the same electric field in my final state. So when I was taking this plate and moving it up, I was doing mechanical work. So in this case, when we were doing it, I was the external agent doing mechanical work. When I moved this plate up, or any other mechanical system which moved this plate up, there was a force, attractive force between the charge on the top and the charge on the bottom. I did positive work in moving them apart. It's like taking a ball which wants to fall down, and when you move the ball up, you increase its potential energy. That's the same thing which happened here. This mechanical work got stored as electrical potential energy now. The mechanical work which went in moving the plates above, that got stored as extra potential energy to be available to be used at a later time. When I had the battery connected, the battery did negative work. The battery was acting like an external agent and bringing the charges back towards itself, and bringing the charges back towards itself, it was reducing the energy of the system. When the battery is not connected, then whatever mechanical work I did, that got stored as extra energy. So remember, again, the energy stored in a capacitor is half q square by c, or half cv square, or half qv. And for the systems we would deal with, thinking in these two equations helps. If q remains constant, And then trying to think of how the energy changes with this equation is more straightforward. And if V remains constant, then thinking in that equation is more clear. When does Q remains constant? When a battery is not connected. And when V remains constant, when battery is connected. That's it for this topic.